Now knowing that there are other galaxies outside of our Milky Way, specifically that all of these spiral nebulae are likely their own entire galaxy, this led people to start searching for more. And as they did, they started to find other types of galaxies, not just spiral types. So we began to classify galaxies based on their appearance. There are three categories. There are spiral, elliptical, and irregular. Alright, here's our first lecture quiz question. What type of galaxy do we believe the Milky Way is? A. Spiral, B. Elliptical, or C. Irregular? Go ahead and think about it and we'll discuss in just a bit. So what kind of galaxy is the Milky Way? The answer is A. It is a spiral type galaxy. Spiral galaxies are these ones with the long, beautiful spiral arms and the disk. These are very similar to the Milky Way galaxy. Out in the disk and the spiral arms, notice that they are bluish in color, indicating that these have to have a relatively young population of stars. So these are primarily population 1 stars. The central bulge is yellowish, showing that they has an older population, likely population 2. Here is our second lecture quiz question. Why is the bulge of a spiral galaxy yellow in color? A. It has a lot of gas and dust, reddening the color. B. The population of stars is older, so all of the blue stars have died out. Or C. The gravity from all of the stars in the bulge has redshifted the light. Go ahead and think about it, and we'll discuss in just a bit. Alright, so why is it that the central bulge is yellowish? It is B. Remember, the first color of stars to die out are blue, and because there's no ongoing star formation in the central bulge, there's no way to keep that young blue population of stars alive. So, with no star formation, the blue stars have died out, which means we're now left with the whites and the yellows, giving it that kind of white-yellow appearance. So the correct answer again is B. As we look at spiral galaxies, we're actually able to subdivide them, to subcategorize them into three different types. There's SA, SB, and SC. And the way we do this is, again, by how they appear. SA galaxies have a large central bulge and a relatively small disk. SBs have a smaller bulge and a broader disk. And an SC has a small bulge and a very large disk. Now, the difference between SA, SB, and SC, the underlying cause, appears to be the amount of interstellar medium. Remember, it's the interstellar medium where stars begin to form what they form from. So, an SA having a relatively small disk likely suggests that it has very little remaining interstellar medium to renew the stars out in the disk. An SB has more interstellar medium, and an SC has the most. Now, about half of all spiral-type galaxies have a central bar instead of a central bulge. Okay, so notice that these are elongated, and then, sweeping off and away from that central bar, we get the spiral arms. Now, so these are known as barred spiral galaxies. And again, we subdivide them as we compare the size of the central bar to the rest of the galaxy. So we have SBA, SBB, and SBC. Now, based off of computer simulations of galaxy formation, barred spirals should actually be normal. We should have mostly barred spirals. But again, we see a mix of about 50-50. Again, according to computer simulations trying to figure this out, what appears to be different between the two, we believe, is the amount of dark matter that the galaxy contains. So we will talk a little bit more about dark matter later, but we do see that dark matter does seem to influence galaxy formation and evolution. Our second type of galaxies are the elliptical. Now notice the overall color from these elliptical galaxies. They are all very yellowish. which suggests that they're going to be dominated by population 2 stars, and they have little or no ongoing star formation, which also tells us they have very little interstellar medium. Now, there's enough variety among these elliptical galaxies that we can, again, subdivide them. We do this by designating them as E0 and then up through E7. So E0, E1, E2, and so on. And E0 is essentially a round ball of stars. Okay, it looks very, very nicely round. Then as we increase in number, the galaxy becomes more flattened and elongated. So out here at an E6, it's more football-shaped. As we look at ellipticals, there's actually a huge range in the sizes that we find for ellipticals. That's actually not true of spirals. All spirals are close to the same size. They're not exactly the same size. They definitely do have variation, but they're kind of close. That is absolutely not true with ellipticals. For example, in this image, we have two examples of what are known as giant elliptical galaxies. Just one of these is larger than 20 Milky Way galaxies. You could fit 20 Milky Ways across one of these things. Okay, they're absolutely incredibly huge. On the other extreme, the very smallest types of galaxies that we find are the dwarf elliptical galaxies. Normally, when we talk about how many stars are in galaxies, particularly with spirals, we do it in the hundreds of billions. Okay, so our Milky Way galaxy has between 200 and 300 billion stars. These dwarf ellipticals, we count in millions. Okay, a few million stars. Now, if you remember back when we were talking about stars, we mentioned that low-mass stars far outnumber high-mass stars. Okay, that they're way more low-mass than high-mass. We actually expect kind of a similar thing to be happening with galaxies, which would suggest that these dwarf elliptical galaxies may actually be the most common type. However, we don't know if that's true. Now, because we can't find them. Now, the problem is, do we not find them because they don't exist, or are we not finding them because they're super faint and very hard to see? This is an ongoing question that we're still trying to figure out. There's a type of galaxy that appears to be somewhere in between a spiral and an elliptical. These are referred to as lenticular, because if you see them on edge, they kind of look like a lens, where it's thick in the middle and then it tapers off towards the edge. Now, these are designated as S0 or SB0. S and SB like spiral and barred spiral, and then 0 like it's an elliptical. So these have a very large, pronounced central bulge, which makes it look very similar to an elliptical galaxy, but it does have kind of a dusty disk surrounding that bulge, which kind of makes it a spiral, but it does not have pronounced spiral arms. So it's kind of in between the two. These are the lenticular. Our last type of galaxies are the irregular. If it's not a spiral or an elliptical, we still have to stick it somewhere. These are the irregular. Only about 3% of all galaxies we see are irregular. Now, there are two types of irregular. We have irregular type 1. That's this image here on the top. These ones are just kind of weird blobs. They don't really have any form or overall structure, but we do see they have stars and interstellar medium, and in fact, this one even has ongoing star formation within it. The other type are the irregular type 2. That's this bottom image. This is the antenna galaxy. As we get a close-up of this galaxy, we can kind of see that it's probably actually two galaxies that are in the process of colliding. So here's one central bulge and there's another. You can kind of make out a disk here and another disk there. So this is two spirals that are colliding. And as they are, their mutual gravity is disrupting their overall shape, forming them into an irregular type 2. So irregular type 2s are highly distorted with weird shapes because of collisions. We can summarize all of this stuff on what is referred to as the tuning fork diagram. Okay, so this is a way of just showing all of the different types of galaxies. We start out over here on the left with the E0 elliptical, these ones that appear just like round balls of stars. Then as we progress towards the right, we increase in number, so E0 to E7, with them becoming more flattened and elongated. Then we have the lenticular. Then we split into spiral and barred spiral, with SA, then SB and SC, and SBA, SBB, and SBC. And then, because we have to include it, we always throw the irregular on, although I've seen them all over. I've seen them here, I've seen them up, I've seen them down. They've been all over the place. But we always throw them on to recognize that they do exist. Now, when Hubble actually first proposed this tuning fork diagram, he actually suggested that it was an evolutionary sequence. The galaxies begin as E0 ellipticals and will eventually form into spiral or barred spiral. Now, based on what we've talked about this, does that seem like a reasonable idea, given all of our information? I really hope you're saying no, because E0s and all ellipticals have very little interstellar medium and no ongoing star formation, meaning they're done. They're no longer doing any of this. Whereas the spiral and the barred spiral still have interstellar medium and also have ongoing star formation, so they're still active in processing. Okay, so there's no way to go from a galaxy with no interstellar medium to somehow create interstellar medium to make it into a younger type galaxy. So, although I see where he's coming from, absolutely not the case given all that we now understand about galaxies.